Hey everyone, and welcome to this explainer. Today, we're going to decode the ultimate playbook of the physical universe. We're taking a deep dive into the fundamental rules that govern literally everything you interact with. This is the absolute foundation of essential chemistry, and I promise you, by the end of this, you're going to look at the everyday transformations happening around you in a completely different way. Let's get into it.
So let's just jump right in with the biggest question imaginable. What exactly is the universe made of? Think about it. When you see a piece of iron rusting on some forgotten bicycle, or when you watch milk slowly turning into curd on your kitchen counter, what invisible choreography is actually happening there? It's so easy to take these everyday changes for granted, but right under the surface, there's this totally fascinating world of substances changing, breaking apart, and recombining. Now, you might think chemistry is all about pristine labs and modern tech, but actually, centuries ago, brilliant thinkers were already trying to solve this mystery. Over in ancient India, within the tradition of Rasayan Shastra, a scholar named Acharya Kanda conceptualized the atom way before microscopes even existed. He theorized that matter couldn't just be divided infinitely, that eventually you'd hit an absolute, indivisible, fundamental particle. Pretty mind-blowing, right?
Okay, here's our roadmap for today. First, welcome to the central science. Second, meet your maker, matter. Third, rules of chemical engagement. Fourth, measuring the invisible, and finally, the math of reactions.
All right, part 1. Welcome to the central science.
So, chemistry didn't just magically appear overnight. It's been a massive evolution. It started off with alchemy, that mystical search for gold and immortality. Then it shifted into itrochemistry, which was all about medicines. And meanwhile, like we just talked about, the ancient Indian tradition of Rasayan Shastra was pulling off incredible practical feats. We're talking mastering metallurgy with copper and iron, developing Ayurveda, and even early soap making and prepping acids like nitric and sulfuric acid. It's like a giant relay race of knowledge that laid the groundwork for the hyper-precise modern chemistry we rely on today.
Moving right along to section 2, meet your maker, matter.
To really understand the changes happening in the universe, we have to establish an absolute baseline here. What is matter? Simply put, it's anything that has mass and takes up space, period. Whether it's the screen you're looking at right now, the air you're breathing, or the coffee in your mug, this is the stage upon which all physical and chemical properties play out. It's the whole shebang.
And it all comes down to how particles are packed together. In a solid, those particles are crammed in tight, which gives it a fixed shape and volume. Liquids, they've got a bit more wiggle room. The particles can slide past each other, which is why a liquid takes the shape of its container. And in a gas, particles are just spread far apart, flying everywhere to fill whatever volume they're in. And the cool part is, just by tweaking temperature or pressure, you can flip between these states. So when we talk about pure substances, we've basically got two camps, elements and compounds. And this distinction is absolutely crucial. An element, like the oxygen you're breathing right now, is made of just one type of atom. It is the universe's purest ingredient. You literally cannot break it down any further. A compound, on the other hand, like water, or H2O, is made of different atoms bonded together. Because it's a combination, it can actually be chemically broken back down into hydrogen and oxygen.
And hey, a quick but super important clarification when we measure this stuff. Mass versus weight. They are not the same thing. Mass is the actual amount of matter in an object, and it is a universal constant. If you fly to the moon right now, your mass is exactly the same. But your weight, that changes depending on gravity. In chemistry, we care about the constant. We care about mass.
All right, part 3, rules of chemical engagement.
You see, the universe isn't just pure chaos. It operates on really strict guidelines. We have 5 foundational laws of chemical combination. First up, the big one, the law of conservation of mass. You can't create or destroy matter, you can only transform it. Then we've got definite and multiple proportions, which basically tell us that elements combine in very specific, predictable ratios. Toss in Gay-Lussac's law for gases and Avogadro's law, and what do we get? We get proof that chemical reactions aren't random magic, they are highly predictable, mathematically sound events.
And it was John Dalton who beautifully wrapped all these laws up into his atomic theory. He proposed that matter is made of atoms, which act like tiny, indestructible puzzle pieces. They can't be destroyed, but they combine in fixed, simple whole number ratios to form compounds. So a chemical reaction isn't the creation of new matter out of thin air, not at all. It's simply the rearrangement of those existing atomic puzzle pieces clicking together in a new way.
Which brings us to section 4, measuring the invisible.
Okay, here's a crazy thought.
If atoms are so incredibly tiny that a single drop of water contains more atoms than there are stars in the observable universe, how on earth do we measure them? Well, meet Avogadro's number, 6.022 times 10 to the 23rd power. Chemists call this a mole. Honestly, just think of it like a baker's dozen, but on a cosmic scale. It's simply a massive counting unit designed to group these microscopic atoms into a batch large enough for us to actually work with. And that leads us perfectly into molar mass, which is just the mass of exactly 1 mole of a substance, weighed out in grams. So if you were to count out exactly 1 mole of water molecules and plop them on a scale, they would weigh exactly 18 grams. It's this beautiful concept that bridges the gap between the invisible world of atoms and the tangible weights we can actually measure on a lab scale.
And because we know this molar mass, we can do some incredible math, like calculating the exact elemental makeup of everyday things. Take water, for instance. It's H2O, 2 hydrogens for every 1 oxygen atom, right? But because oxygen atoms are just so much heavier, oxygen actually makes up nearly 89% of water's total mass. Hydrogen is just chilling there at around 11%. Molar mass literally gives us the power to see exactly what percentage of a compound belongs to which element.
Finally, Section 5, the math of reactions.
So how does a chemist actually figure out the formula for a brand new compound? It's a super logical step-by-step process. Step 1 is finding the empirical formula. This tells us the simplest, most basic ratio of the atoms present based on their mass. But that doesn't always tell the whole story. So Step 2 uses the compound's molar mass to determine the molecular formula, the true actual number of atoms in the molecule. It's basically like figuring out the basic ratio of flour to sugar and then scaling it up to find the exact recipe for the entire cake.
And speaking of recipes, we have to talk about stoichiometry. I know, big word, but it is the ultimate mathematical tool in chemistry. Step 1, identify your reactants. Step 2, use balanced equations to calculate the exact quantitative relationship between them. And Step 3, predict the exact amount of product you're going to make. Stoichiometry is how chemists know precisely how much of substance A they need to mix with substance B to get the absolute perfect amount of substance C without wasting a single drop. It's a real game changer.
But let's be real, the world isn't always perfect. Sometimes you run out of stuff. Enter the limiting reactant. This is the reactant that gets completely consumed first in a reaction. Let's connect this back to baking that cake. Imagine you've got 100 eggs and 10 pounds of sugar, but only 1 single cup of flour. It absolutely doesn't matter how many eggs you have. The moment you run out of flour, the baking stops. Flour is your limiting reactant. In chemistry, the ingredient that runs out first dictates exactly how much final product you can possibly make.
Wow, okay. We've zoomed all the way from ancient philosophers predicting the atom, right up to calculating the exact mathematical outcomes of invisible reactions using stoichiometry. Chemistry really is the central science that built our modern world, from the fertilizers that grow the food we eat to the life-saving medicines in our hospitals. So I'll leave you with this final thought. If mastering these fundamental rules and formulas unlocked all of that, what invisible boundaries is chemistry going to break next? Keep questioning, keep learning, and thank you so much for joining me on this explainer.